In this video, we are going to look at parametric equations. We're going to plot a curve described by a parametric equation. We're going to convert parametric equations of curves of the form y equals f of x. We're going to recognize parametric equations of basic curves such as lines and circles. And then we're going to recognize a parametric equation of a cycloid. So imagine, if you will, a bug is crawling across the tabletop, starting at point O and then walking along, tracing the curve C until it goes on to wherever it goes to. Now notice that this curve, if we start at O, it's got a direction in which the bug is doing its little dance or walk across the table. So not only is it following some curve, but it also has a direction involved with it. Now, if we take a look at the way that this is set up, my point at any given time of where the bug is on the table is x, y, but it is a function of time. It is the f of t and the g of t. So it is dependent, the place in which the bug is dependent on the time. So the independent variable is time. It is neither x nor y. So what we end up with is a system where x and y are dependent on some other variable, and that other variable happens to be independent. So it can be noted as f of t or x of t, where t is the independent or the argument, and y is equal to g of t or y of t, again, where t is the independent or the argument. We call this a system of parametric equations, or we have parameterized some given curve. In this case, it's the curve C in which the bug was walking across the table. Now, as t varies over the interval I, the interval I, the functions of x of t and y of t are generated, and they produce the ordered pairs x, y that produces the graph. X is the variable that is associated to x of t of the parametric equation. So now let's define it formally. If x and y are continuous functions on some t, in functions of t on some interval I, then the equations x is equal to x of t and y is equal to some function y of t. And we call these parametric equations where t is the parameter. It is the set of the points x, y obtained as t varies over the interval I, and it is the graph of the parametric equation. The graph of the parametric equation is a parametric curve or a planar curve, and it's denoted by C. If we're asked to graph these by hand, and we can also do this in Desmos, but if we're asked to graph these by hand, then what we want to do is we want to pay attention to any restrictions there might be on t, because t is our independent. Now, if we note that t is less than or equal to 1, then we're going to write an ordered pair chart almost. So we're going to put in t is our independent, and we can choose -1, 0, 1, t is less than 1. I just went right to the one I'm used to doing. So I have -1, again, man, hello, 1, 0, -1, -2, and -3. Then I have a value for x. X is going to be equal to t squared plus 2t plus 1. And then my last one is t plus 1, which is my y value. So I choose a value for t and I plug it into those other 2e functions. So I put in 1 and I get 1 squared plus 2 plus 1, which gives me 4. I put in 1 for the second equation, the y equals t plus 1, and I get 2. So over here I'm going to go to 4 and 2. So here's my point. Now I'm going to choose 0. So I'm put in 0, I get 1 out and 1 out, so 1, 1 comes out. So 1, 1 as the xy ordered pairs. I put in -1, and I'll have, when I put in -1, I'm going to have 1 minus 2 plus 1 gives me 0. And then I would put in 0 here, and I get 1. So I am 0 for the x and 1 for, I put in, good afternoon. I put in -1 for the second one, and the second equation, and I get 0 out. And I would continue doing this, and what I'll get is a graph that looks like this. Now, the other thing I need to put on there is as t increases, how does my graph go? Well, now I started out with a +1, then 0, then -1, -2, then -3. So I'm going to read it this direction because t is increasing. So as t is increasing, I'm actually moving along the curve in this direction. So when we're doing parametric curves, we also not only do we want to graph what it looks like on the xy plane, is we also want to note how the, if you will, the bug is moving along that curve. So these graphs will have directionality. Now let's take a look at C. Now this has an ordered pair, or this has a set where we're going to start with t between 0 and 2 pi. When I see that, that typically means I have a conic of some sort. So once again, I have my t. I have my x, which is equal to -1 plus 3 cosine of t. And then I have y is equal to 4 sine of t. Now I'm going to first start out with easy angles that I know the values of without doing much in terms of fractions or decimals. So I would probably start out with 0, the quadrant angles, 0, pi over 2, pi, and 2 pi, and see where I am. If I don't have enough information at that point, then I might have to go back and choose some other values for t. So when I put in 0, the cosine of 0 is 1, so I have -1 plus 3 happens to be 2. I put in 0 for sine, so sine of 0, which is 0. So my first ordered pair is 2, 0. So I'm going to go ahead and put that one on there. Then I have pi over 2 with the cosine of pi over 2 is 0. So this will just be -1 plus 0. And then, of course, the sine of pi over 2 is 1, so this is 4. So I have -1 for my x, so -1, and +4 for my y. So that's where that part is. Now I'm going to do pi. When I put in pi, I'm going to end up with cosine of pi, which is -1. So I have -1 minus 3 more, which is -4. I put in pi, and I have 0. So I have -4, 0. I'm going to put in 2 pi. Well, 2 pi is the same thing as putting in 0 in terms of sine and cosine values. So this goes back to 2 and 0. So what it looks like is happening is it looks like I have some sort of half of a circle, possibly. Maybe I have an ellipse. Oh, guess what I forgot? 3 pi over 2. So I put in 3 pi over 2, and the cosine of 3 pi over 2 is 0. So this gives me a -1, and then the sine of 3 pi over 2 is a -1, so that gives me -4. Oh, looks like I have an ellipse. Now, paying attention to the way I am moving along, I'm moving along like this. So as t increases, the direction I am going is in this direction. So that's what a parametric curve would look like. And don't forget the way in which we are moving in terms of t increasing. Now, the other thing that we want to do is be able to eliminate parameters. Now, these curves are parameterized, and sometimes it's easier to sketch the graph when it's just in terms of x and y. Now, to eliminate the parameter, what we do is we try to decide which one is going to be the easiest to solve for in terms of x or y. So I'm trying to get t equals. That's what I'm trying to get. So I'll start with x is equal to e to the t. Now I think about the fact that this goes back to pre-calculus 1. If I take the natural log of both sides, then I have this rule that says the natural log of e raised to the x is equal to x all day long in general. So I know the natural log of x is going to give me just t. So now I have a replacement to put in to my second equation. So to put this into my second equation, I'm going to have y is equal to e raised to the 2, the natural log of x. Now we also have this other rule back from pre-calculus 1 that says if I have the 2, the natural log of x, this is the same thing as the natural log of x raised to the 2. The exponent goes on the variable, not as the natural log of x, the quantity squared. It is on the variable itself. So this is the same thing as e raised to the natural log of x squared. However, we also have another rule that says if I have e raised to the natural log of some b value, then this is going to be equal to b. So this tells me that this is just going to be equal to x squared. So y is equal to x squared. That's what it looks like in terms of my Cartesian plane. Now, before we get all excited and draw the entire quadratic or parabolic shape, we do need to think about the fact that when we go back to where we started. Now, when I look at these two equations when they've been parameterized, when I put in any value for t, x will always be a positive number. Let me say that again. When I choose any value for t, x will only be positive numbers. And the same thing for y. So that tells me I don't get the entire parabolic shape. I only get half of the parabola. And so it's going to look something like that. Now, the other thing I have to pay attention to is as t increases, which way am I going? Now, I put an arrow on there because that's that tells me that my parabola is going up forever. But what is the directionality of that? Well, that's a different question altogether. So I just need to see what happens when I choose some pairs. So let's go with t, e of t, e of 2t, because this is my y value, this is my x value. Let's choose 0. So when I put in 0, I get 1. When I put in 0 here, I get 1. Let's put in 2. When I put in 2, I'm going to get e squared. When I put in 2 here, I'm going to e to the 4th. So this tells me, indeed, I am actually moving in this direction. So do pay attention to the fact that even though you eliminate the parameter, that does not mean you're going to get the entire parabolic shape or the entire Cartesian shape. Let's take a look at my next example here. Now, the first thing we want to pay attention to is the fact that these both have 2 pi. So they're 2 theta. So they are the same angle. And that's important because what I'm going to do is I'm going to solve for sine, I'm going to solve for cosine. So I have x over 6 is equal to the sine of 2 theta, and y over 4 is equal to the cosine of 2 theta. Now we also have this other rule that says the sine squared of some alpha plus the cosine squared of some alpha is equal to 1 all day long. That's true. It's a Pythagorean identity from pre-calculus 2. So that means x over 6, the quantity squared, plus y over 4, the quantity squared, is also equal to 1. So that tells me what I have is an ellipse centered at the origin with a shape that looks like this. I'm going to go out 6 in this direction in the x's. And this goes again back to pre-calculus 2. I'm going to go out 4 in each direction on my y's. And so it has a graph that looks something like this. Now I'm going to go back here. I'm going to say now, when I have the theta, because sine and cosine can take on any, this is in calculus, so we're only talking about radians, I can put any radian value in here and a real number will come out. So there is no restrictions on the domains. So then what we're going to have to do is think about what is my directionality. So what I'm going to do again is I'm just going to choose like 0. So I'm going to put in 0. And so I have the sine of 0, which is 0. And it gives me 6 times 0, which gives me 0. And then I'm going to put in 0 here. When I put in 0, I have 4. So I know that I'm going to start right here. Now I'm going to put in pi over 2. And again, that's increasing on my theta value. Now notice it's theta, not t, and that's okay. So what I'm doing is I'm doing a chart with theta here. X is equal to, and y is equal to. I put in 0. I have 0 here and 4 here. So my ordered pair is 0, 4. Now I'm going to put in pi over 2. When I put in pi over 2, then this is going to be the sine of pi, which again is 0. And then I'm going to put in pi over 2 here, which is the cosine of pi, which is -1. So that's a -4. So I went from Well, that didn't help me much. I went from here to here, but I still don't know the directionality. So let me put in pi over 4 so I can get a better idea which way I went. So I put in pi over 4. Well, 6 times the sine of 2 pi over 4, so 2 times pi over 4 is going to give me pi over 2. So I put in pi over 4, and I'm going to get 6 out. And then this one gives me 0. So what I know, because pi over 4 is between 0 and pi over 2, is I started here, and then I went to a 6, 0. So I must be going in this direction. Okay, now let's take a look at my next one. Once again, what I'm going to do is I'm going to choose the easiest one to work with. Before, what I did is I solved for my my t that was associated with the x. This one may not be the easiest way to do that, so I think what I'll do is I will solve for the t that's associated with a y, because that seems like it's probably going to be a little bit easier, maybe. So I have x is equal to the natural log of 2t, and then I'm going to write this as the square root of y is equal to t squared. Now, I don't have to really worry about the plus and minus part, because my t here, I can't put in negative numbers. And in fact, not only can I not put in negative numbers, I can't even put in 0 here. I can't take the natural log of 0, and I can't take the natural log of a negative number. So I know, without doing any work, this part right here tells me that t must be greater than 0 to begin with. So if t must be greater than 0 to begin with, then I know I don't have to worry about putting on the plus and minus on this square root of y, like I normally would have to do. All right, so now I've got a value for, I'm going to take the square root of this too, as I have a value for y. So the square root of y is equal to t. So then that tells me that I have x is equal to the natural log of 2 times the square root of y. Now what I have is a function in terms of my independent being y and my dependent being x. But if you're like, man, I really don't like that, that is totally fine. What you could have done is you could have taken this equation and solved for t. So if you don't like this, that's totally fine. The restricted domain is still there. This part right here tells me I still have that t has to be strictly greater than 0. To eliminate the natural log on x is equal to the natural log of 2t, what we're going to do is we're going to take each side and raise it so it is e to the x and e to the natural log of 2t, which gives me e to the x is equal to 2t, which gives me 1/2 e to the x is equal to t. Now that allows me to substitute it into this one. And so I have y is equal to 1/2 e to the x, the quantity squared. Excuse me. So y gives me y is equal to 1/4 e to the 2x. And so that might be a little easier to solve for. Now remember, I cannot put in anything less than 0. I can't put anything in less than 0. So I could put in fractional parts, but I won't be able to put in anything less than 0. So when we think about what this graph looks like, if I put in any fractional less than 1, this part of x is going to go to negative infinity. And t, if t is any fractional number less than 1, y is going to approach 0. So we know that that part of the graph is t goes to a fractional part between 0 and 1. As t gets closer, as you want to say the limit, as t goes to 0, my x value is going to go way down to negative infinity, and your y value is going to get really, really small. Now the graph of 1/4 e to the 1/2, well, I'm going to squeeze in my graph here. It's actually going to cross right here at 1/4. Now that's not drawn to scale because it's really, really small to see. And the graph itself is going to look something like this. It's an exponential graph. It's going to look something like that. Because that's what the exponential looks like. Now, we need to know which direction it's going. I put arrows on both ends so that I know it's going in each direction forever. But I need to know the directionality. So the way I'm going to do the directionality is I'm going to choose easy numbers. I'm going to choose, again, I have t, x, and y. I'm going to choose t to be 1. So this becomes the natural log of 2, and this becomes 1. Okay? So then I have the ordered pair, which is a natural log of 2, comma 1. Natural log of 2, comma 1. So natural log of 2, comma 1. Now, if I choose, say, 5, so t is equal to 5, I'm going to get the natural log of 10, and I'm going to get 5 squared, so I'm going to get 25 out. So that tells me as t increases, my direction of my parametric curve is going in that direction. It's also increasing. As t increases, so does the direction of my graph. Okay. Again, what we're asked to do is we want to convert from parametric equations into rectangular form. So we kind of done a few of these. We need to pay attention to where t is located. So t is in some interval. And this is going to take on, just like we did before, some elliptical shape. And the reason I know that is because we're going to use the same rules as we did before when we had 2 theta. So x over 4 is equal to the cosine of theta, and y over 3 is equal to the sine of theta, knowing the fact that sine squared theta plus cosine squared theta is equal to 1 all day long, which means I have y squared over 9 plus x squared over 4 is equal to 1, and if you prefer, you can rewrite this as x squared over 4 plus y squared over 9 is equal to 1 if you prefer that. Either way, same kind of thing. Now, let's take a look at b. With b, t is greater than -1, and that's because of where it's coming from. So first of all, t cannot equal -1 because that'd be undefined here, and it'd be undefined here. If t is on the left side of -1, I wouldn't be able to do this because it would be a complex number. So that's where that t is greater than -1 is coming from. So once again, I'm going to choose the one that's going to be the easiest. We typically have y equals. I think it'd be easier to solve for t on the x part because notice on this I have a t here and a t here. So I think this one may be the easier one. So what I'm going to do is I'm going to go ahead and square both sides. And when I do that, I get x squared is equal to 1 over t plus 1. Multiply both sides by t plus 1 and divide both sides by x squared. I get t plus 1 is equal to 1 over x squared. So that tells me that t is equal to 1 it's 1 over x squared minus 1. Now all I have to do is put that into here. So I have y is equal to 1 over x squared minus 1 over 1 plus 1 over x squared. I'm going to multiply everything by x squared to just get rid of my complex or nested fraction. And so I get 1 minus x squared over x squared plus 1. And there it is. Now, I remember, don't do any illegal cancellations and say my x squareds cancel. They don't. My 1s, they cancel. They don't. That's as good as that one gets. Now, let's take a look at my next example here. I have x is equal to t cubed. So I'm going to write this as t is equal to the cube root of x. So I'm going to put that into my other equation. So y is equal to 3, the natural log of the cube root of x. I'm going to write this as y is equal to 3, the natural log of x raised to the 1/3, because that's equivalent. I'm going to use my laws of logs that says this thing comes up and becomes a power on the x raised to the 1/3. And so I have the natural log of x raised to the 1/3 raised to the 3, which means that I have the natural log of x. And that's it for that one. Typically, because of the fact that we have t has to be greater than or equal to 1, We don't have to necessarily put on the absolute values there because this is already going to be restricted because of this t. Last one here. Now, with this one, I have x is equal to the tangent of t and y is equal to the secant of t minus 1. Now you're thinking, wait a minute, how am I going to deal with that? Well, this is how you're going to deal with that. We're going to square both sides. We have x squared is equal to the tangent squared of x. Now, we have a Pythagorean identity that says the cosine squared of theta plus the sine squared of theta is equal to 1 all day long. Equivalent for tangent, I have 1 plus the tangent squared of theta is equal to the secant squared of theta. So using that bit of information, wherever I see tangent squared, I'm going to replace with x squared. So I have 1 plus x squared. Now, I have secant squared right here, or secant squared. So if I take this and say y plus 1 is equal to secant squared of t, then I can replace that secant squared with 1 plus y. I can subtract y from both sides and I get x squared is equal to y, and I am done there. All right, so that's just going and converting from parametric into Cartesian. That's going to help us decide what's going on, whether or not I have a line or a parabola or an ellipse or a circle or a hyperbola. So again, this is going back to your pre-calculus 2 in terms of shapes. So here is what I have. Now I know, without doing any work, this is going to be an ellipse because we've done a couple of them. So we know this one is going to be ellipse. Let's just confirm this. X over 2 is equal to the cosine of 3t. Y over 5 is equal to the sine of 3t. We know that the cosine squared of any angle, in this case happens to be 3t, plus the sine squared of any angle, again, happens to be 3t equals 1. So we have x squared over 4 plus y squared over 25 is equal to 1, and we know that this is an ellipse. So what about the other one? Well, let's go ahead and do the other one. I haven't done one like this one before. So doesn't matter. Let's just solve for t for the first one. And so I have x minus 4 divided by 3 is equal to t. Plugging that into my other equation, I have y is equal to 5 times x minus 4 divided by 3 minus 2. Oh, that's an equation of a line. It's not a nice one, but it is definitely an equation of a line. So this is linear. Now, we have spent time taking it as a parameterized curve and turning it into Cartesian. What if it's in Cartesian and it's beneficial and helpful to put this into parametric equations? Here are some things that we can do. So if you have a function, and the easiest way to do this is let x equal t, and then y will be a function of t. That's a nice, easy way to do it. Now, if you have a function where it is a function where y is the independent, you could let x equal g of t and let y equal t. It just depends on which one's easier. If you have a directed line segment, and that could happen, so you start with your initial point and you end with a terminal point, then the way that you would do that one is you say x is equal to x naught, that's your initial point, plus the difference in those two times t. And the same thing similar to y, where t is going to be between 0 and 1. Now we know how to parameterize the circles up above, but what happens if we have an ellipse that's not centered at the origin, or a circle not centered at the origin? Then we can parameterize it this way with x is equal to h plus a cosine of t and y is equal to k plus b sine of t, where t is going to go between 0 and 2 pi. What will happen by default is that it will be counterclockwise in terms of its orientation if we parameterize in this way. So our first example here is we have a directed line segment. We start at 3, -5, and we go to -2, 2. So from our formula up above, we have x is equal to our initial point, our initial x value, which happens to be 3, plus, and it's going to be the negative 2, and then it's going to be minus 3, because it is going an ending point minus your initial point times t. So this gives me 3 minus 5t. Similarly, for the y, I have my initial point, which is negative 5 for the y, plus my ending y value, which is 2, and then minus a negative 5 times t, which gives me negative 5 plus 7t. And that's it for that one. Now, what about the curve? Well, for the curve, the easiest way to do this is say, oh, we have x is equal to t. That gives me y is equal to 4 minus t squared. That is the easiest way to do it. Now, what about the orientation, or what about the restriction on t? Well, if I say that x is going to go, if x is equal to t, that means t has to run between negative 2 and 2. Oh, and this one up above, it's a directed line segment. We have that restriction on t. What about the circle? Well, first thing we have to do is we have to kick back and say, well, wait a minute. This is not in the correct form. So we have to put it in the correct form. So we have x squared plus y squared minus 6y plus 36 is equal to 36. We have to complete the square. So we have x squared plus y minus, that's 9, excuse me, that should be 9, not 36. 9 here and 9 here. So y minus 3, the quantity squared, is equal to 1. And we know that x is equal to, it is my x part of the center, which is at 0, plus my radius, which is 3, the cosine of t. So in other words, it's just 3, the cosine of t. And then my y is going to be the y part, or the k, of the center of the circle, which happens to be 3, plus 3, that's the radius, the sine of t, which gives me just 3 plus 3, the sine of t. And of course, since this is a circle, then it really doesn't matter how far we go, but we do need to go all the way to 2 pi, so 0 to 2 pi. We can go more than that, but it's really not necessary to go beyond that value for t. Now, there are going to be times, however, in which we are going to want to reverse the orientation or shift the parameter. So here's an example in which we want to, here's our orientated curve. The curve is x squared, x is equal to y squared minus 9. And we want to go from 0, 3 to negative 5, 2. And we want to shift the parameter so that t equals 0 corresponds to 0, 3. So we start out with y is equal to t, and x is equal to t squared minus 9, where t is going to go between negative 2 and 3, because those are the values for the y. But that's going in the wrong direction. If that's going in the wrong direction, we're going to let y equal negative t. That will get us the right direction. And still, we have x is equal to t squared minus 9. Now, all that did is change the direction so it starts at 2 is greater than t, which is greater than or equal to negative 3. So all that's done is multiplied my domain of t by negative 1, which gives me this. It just changed the direction of my inequalities and changed the signs on my 2 and that negative 3. That gives me the right direction. Now, I want to shift this. I want to shift this so that when I have my value, so when I put in t equals 0, it starts at 0, 3. So it corresponds to 0, 3. So to make this shift, what we're going to do is we're going to write this as y is equal to negative t plus 3, because I need this to be 0. So I need to add 3 to it. And so my x then becomes x is equal to negative t plus 3, the quantity squared, plus minus 9. And then this will then become the t squared minus 3, the quantity squared minus 9. And the reason that happened, just a little bit of algebra, and you're like, what? So negative t plus 3, the quantity squared, is the same thing as negative 1 times t minus 3, the quantity squared. So I have negative 1 squared and then t minus 3 squared. And so anyways, here are my two parametric equations. And that's it for this video.